It begins. This is the electric field, magnetic field unit of the course. It does relate a lot to electromagnetism, what we did in grade 11, but I'd say it's infinitely harder because we are adding math to everything. The math it's hard. I tried to book into this unit. There's 2 problem sets. But I can't stress enough the importance, I know most of you won't do this, but you should, of going back and reviewing the examples, not just doing the problems sets and thinking that's enough, but using the extra time that I've built into this unit, excuse me, to go back, redo the example problems, ask me questions about what you didn't get in the example problems, because I can't put into the problem sets everything that you need to know. Otherwise, I'd be giving you 30 question problem sets instead of 10. And it's, it's a tough unit. It's the toughest one I've got. And anything that I teach, this is the hardest stuff. Not necessarily today's lesson, but overall over the course of the unit, it's hard. You can't picture it. You're all capable, but I really can't stress enough the importance of reviewing, redoing the examples. Just, you might think, oh, I've seen the answer before. Trust me, you won't remember. And plus, my test questions are like my examples. So please do yourself a favor. Do great on this unit by not just doing the problem sets, by doing the example problems and asking me questions about the notes, not just what you can't do on the problem sets. It's not good enough, okay? Anyway, here we go. So Coulomb's law. It's the law we give to electric force. So Charles Coulomb, there's probably a Coulomb in the class, I can't remember, but there's usually a Coulomb in the class, and he basically came up with this relationship, and I hope by looking at it, it looks kind of sort of familiar, like something you've seen before, and we'll talk more about that later. But what we've got here is electric force is what we're calculating, and you can calculate electric force using K, which is a constant. So often in physics we use K, and it's K. So it's a constant. We'll figure out K later. Q is the symbol we give to electric charge. So we, I think in grade 11 we did some stuff with electric charge. It was capital Q. Whatever the reason is, textbooks and such, we use lowercase q, okay? So this is the electric force between 2 objects that have electric charge. Okay, and the 2 objects, one of them has an electric charge of Q1, and the second one has an electric charge of Q2. And then it's divided by the distance between, the square of the distance between them. Okay, and again, it's a center to center distance. And I said again because you've used this before, right? And hopefully you're thinking about that right now. Okay, so this K, it's a constant. It's going to be the same the whole unit. It's not spring constant, by the way. I guess you just have to accept it, that sometimes we use K for different things, just like capital T gets used for period and tension and time and temperature and whatever. If we're talking about electric fields, electric field constant is 9 times 10 to the 9. And the units are weird ones, okay? Newtons times meter squared per Coulomb squared. C is the unit for charge, electric charge, which is called the Coulomb. Okay, so K is a constant. That's what it is. It's the number. It's the number you put into this equation. So the idea is that, someone along the way did this. They actually measured electric force and plotted that with an x-axis, an independent variable of the product of the 2 charges divided by the square between them. And when they did that, lo and behold, they found the slope was this, no matter what the objects, no matter what the distance, no matter what the charge is, etc., etc. True for all charged objects. Maybe they got the idea from Sir Isaac Newton. I do not know. Okay. So just understanding electric charge, it's a weird property of matter. And it's certainly a property of all matter because every atom in our body contains charged particles, right? We're just a bunch of charged particles, right? Not neutrons, but electrons and protons, electrons and protons. And protons are made up of even smaller charged particles called quarks. When we measure electric charge, it's just the difference between the number of electrons and protons, right? If there's more electrons, it's negative. If there's more protons, it's positive. We give it the unit C, which is coulombs, and 1 coulomb represents an object having an excess of that many, a whole bunch of electrons, or fewer of that many electrons. If it has an excess of, it'll be a negatively charged object. If it has fewer, it's a positively charged object. And so what I'm saying here is, therefore an object has that many more electrons and protons, its charge is minus 1c. Minus because it's a negatively charged object, right? And it has more electrons, therefore it's minus, right? If it has more protons, it's positive. So I'm sure you remember this, it's sort of a common thing, the law of electric charges. If two objects are positive or two objects have the same charge, they repel each other, and if they have opposite charges, they attract each other. Okay? So you probably remember that. Okay, so let's use let's do an equation. Let's use the equation. It says two small spheres have equal and opposite charges of whatever that is, right? And we'll talk about that in a second. We know their distance, they're separated by 20 centimeters, and the positive charge is on the left of the negative. And I want to determine the magnitude, which is the quantity of charge, and the direction of quantity of force, the Newton's number, and the direction of the electric force. So first of all, something you need to get used to in this unit is the microcoulombs. And again, reusing symbols, because you're thinking micro, this symbol here, is that like friction or something like that? Not even close. Nothing to do with friction. It is the same symbol, mu, but when it's used in front of a unit of measure, it means micro. And micro means a millionth. And because charges typically are small numbers, we use micro all the time. So one microcoulomb is times 10 to the negative 6 coulombs. And you'll just get used to working with that, and we use it all the time. Okay. Yeah, and so a micrometer, which actually has a special term called micron, is a millionth of a meter. So micro gets used all the time. When I worked at FAG, we measured with a lot of precision because we were making bearings, and they had to be to the micron. They're usually the tolerance was plus or minus a couple microns. Anyway, so all we're doing here, we're looking at electric force on the positive charge. So if I draw it out, they're separated by 20, and the positive's on the left. So here's my positive charge, here's my negative charge. So it's 1 microcoulomb, so it's really 1 times 10 to the negative 6 coulombs. So if you're given that micro, just take whatever you've got, whatever number it gives you, and multiply it times 10 to the negative 6. Okay? We know the distance right away. I put it in meters because we don't deal with centimeters. And when we're looking at magnitude, we're only looking at, we're saying no direction. We just want to know the the size of the force, right? And that's just applying the formula. Okay? Some important notes, this is maybe the most important, is like see how the Q1, Q2 is negative? I don't put the negative in there. When you're doing this calculation for FE and we're looking at magnitude, we're looking at size only. We don't care about the fact that it's negative or positive, okay? So you just take the numbers, substitute them in, no negatives, and you get, in this case, 0.23 newtons. Now we want to know the direction. We want to know the force with direction. And this is where, in this unit, you have to apply common sense. And the common sense in this case, when solving for magnitude, it must be positive. Excuse me. When we're doing the direction, you have to say, okay, I'm looking at the force being applied to Q1, and it's due to this one. And you have to say to yourself, well, what way would that be? Well, if nothing else was going on in the universe, only these two charges sitting here, this charged object would feel a force towards the negatively charged object because opposites attract. And that's how you figure out the direction of force in electric force. Okay? So I just got this down here. We're asked to find the force on the positive charge. So the way we do it, I mean, this one was pretty easy. We figured it out, I told you already. But, you know, the proper thing is decide on a positive direction. You know, you say left or right, whatever, right? Determine which way that charge would move if free to move. So this one would move to the right. So therefore, I'm calling it positive, or I can just say right when I add my direction. Okay, very difficult to put, by the way, a check mark on this stuff, because we're talking about some charged object. I don't even know what it is, right? You start to get used to numbers that make sense. Like when we find charges, they're usually times 10 to the negative 5 or 10 to the negative 6, but we don't know that yet. Hard to say what's a good answer, but that's how you do it. Okay, let's do one more example, and then I'll end this video and we'll do another one. I'll make another video for the rest of the stuff. So, applications of Coulomb's law, example 2, this time 3 small spheres. Another reason, by the way, this unit is difficult, because we're not talking about cars anymore. We're not talking about people. We're not talking about things that you can see. We're talking about, I don't know, 3 small spheres, whatever they are. Okay, we do have one lab, which is an application of Coulomb's law, but anyway. So say I've got my 3 small spheres. You just have to deal with it, I guess. And in an order of A, B, and C. The things I know, sphere A has a charge of plus 2 microcoulombs, so plus 2 times 10 to the negative 6. The second one has a charge of minus 2, and the third one has a charge of plus 5. And I want to find the net force on the one in the middle. So if these were just allowed to live here, say the mass was negligible, and so there's no mass gravity attraction at all. It's just electric force, and which, by the way, compared to electric force, gravity is negligible. But anyway, I want to know which way this is going to feel force and how much. Well, what you do, it is a vector sum, right? So the net force on B will be the net force on B due to this one, plus the net force due to this one. And they're vectors, so it's not just adding numbers, though. We have to, in this case, take into consideration the signs. So, when I start, just leave this blue writing for a moment. What I do is I just say, okay, this is just repeating this, right? And then I put in the formula, QA, QB, RAB squared, the distance between them squared. I don't put, like, any signs there yet. I don't know what sign they're going to be. But this is what I do here in the blue writing. I decide what's positive. So I must have said that right was positive. I usually do. Did I put it down anywhere? Yeah, so I said right was positive. Okay? So I decide on a positive direction, step 1. And then, when I figure out what sign to put on this one here, I say, okay, pretend that C didn't exist and these were the only 2 that existed. I'm looking at the net force on B. Which way would B move if these were the only 2 that existed? Well, if B were free to move, it would move towards A, so it would move in the negative direction. So I give it a negative sign. You can hardly see the yellow, but it's there. And likewise, I do the same thing over here. I say if B was free to move, it would move, actually in this case, in the positive direction. It would move towards C, because C is positive, right? So I put a positive there. So that's really, the colored signs, that's really important to get a hang of. That's why I think this example is worth doing again when you start studying, is redoing this very example, because it's a good one, and I often use this as a test question. Okay, so I figured it out here. And then I put in the numbers, so I keep that negative, right? That just follows down here. Notice I multiplied them both by times 10 to the negative 6. So anytime you see microcoulombs, just add a times 10 to the negative 6. The distance is just the distance between each one. And remember, no negative signs inside up here. The only time you apply any signs is when looking at, these ones. Okay? Once you're done that, you work it out, and it ends up being right. Now, we might have made a prediction when we started, which way do we think that this thing would move based on the sizes of the charges and the distances, and let's see what we would predict. Looking at this, well, B is closer to A, so it might feel a stronger force, right? It's a little bit further away to C, not that much further though, and C is a much bigger charge, right? It's more than 2 times the charge, so it's actually a little bit hard to tell because there's offsetting things, but I know, you might say, well, that's much bigger, so probably it'll be a little bit to the right, and in fact it is. So I think that number makes sense. So I'm going to put a little check mark on that baby, and that's calculating electric force. That was a long video, and I'm not even done for Coulomb's law, but at the first bit, and again, please put a star beside this example. You need to redo this example before you write your unit test.